Hi, this is Chris Kiefer, and welcome to the Power of ERDC podcast. Even in the age of modern supercomputing, engineers still demand tangible models to fully understand the complex interaction between coastal infrastructure and ocean forces. On today's episode, we are examining ERDC's unrivaled ability to build scaled representations of real-world systems and use them to evaluate civil and military project designs. Joining us to discuss ERDC's coastal physical modeling and testing is Dr. Duncan Bryant, a senior research hydraulic engineer with ERDC's Coastal and Hydraulics Laboratory. Duncan, it's great to have you here today.
Thanks for having me.
Yeah, absolutely. I guess maybe we ought to start by kind of explaining the topic and kind of introducing everyone to physical modeling for our audience who may not be familiar. Can you explain what physical modeling is and why it's needed for civil works and military projects?
Sure. So physical modeling is basically a representation of a larger project usually. So what I mean by that is I want to know how a seawall is going to perform, or a road-mounted structure is going to perform, or military assets going to perform. It's very expensive to build those things at full scale, and in the real world and test them. So what we do in a physical model is we actually do what we call scale down. So we actually make that smaller, and then we're able to test that and preserve the critical physics. And that's the key. So the physics haven't changed, but how we do it may, but overall we can do those scale tests and help inform decisions and designs.
Sure. So of whatever that structure is, it's just it'll look just like it. It'll, maybe more importantly, respond just like it and do it. And we'll talk more about the facilities you have, but you've got various flumes and basins and whatnot that you'll put the structure in that body of water.
Yeah, that's correct.
And use it to kind of test how it'll respond before you actually build the giant dam and see what it's going to do.
Yeah. So you can think about it like, obviously, we're interested in how water moves, whether it's through riverine processes, through a lock chamber, or in a coastal environment, how waves may force a structure, So we have different facilities to test those models in. So we have, we can replicate the physics involved with all those different processes at a smaller scale. And there's some rules involved that make that possible, and there's some things you have to keep in mind. But in general, you can design the model at a smaller scale much more affordably than you could a large scale or an actual thing. You can test it, you can make changes, oftentimes very rapidly make changes to find out, okay, does this work? And then you could iterate in a laboratory type setting and then figure out, okay, this is the best design, or we know this design will work. And then you can move forward with the process of maybe either building or acquiring that solution.
Yeah, sure. It's really important step in the process. And probably good to note here, I mean, this isn't a recent thing that ERDC has jumped into all of a sudden.
No.
This kind of goes all the way back to ERDC itself is almost 100 years old. And this is kind of what really ERDC in a lot of ways started doing.
Yeah, I mean, when you look back at ERDC's history as waterways, right, when we were Waterways Experimental Station, the first thing we were really doing with these types of models. So in a lot of ways, it's like people kind of maybe are in awe that we're still doing them, that we still do this type of work. But what I'll say is, again, the physics haven't changed, but how we do it has changed dramatically.
Yeah, and so I wanted to ask on that exact point. So like you said, people wonder, so now today's environment, computers become more powerful, the ability to do simulations becomes more powerful. Why is physical modeling still necessary?
Well, there's some problem sets that even though we could do them computationally, it may not be as efficient or effective. And really, it's not either or. And that's one thing that's important to note is that it's not always, okay, I just want to do a physical model. I don't want to do a numerical model. The best solution oftentimes today is to do both. And why that is, a lot of times has to do with the fact that we could iterate in a physical model and visually see what's happening. That's a really important component, is you can show, you can see, sometimes you can even touch the solution. And then you can go back, and replicate some of those things in a numerical type space and even refine it further. So really the union of the two provides a lot more power in deriving solutions.
Sure. And I guess there's 3 tools, I think is what you were telling me the other day. So we mentioned physical modeling, numerical, which of course is just taking computer simulations, and then field data collection as well, and kind of all 3. Can you kind of talk about how those 3 maybe build on each other, work hand in hand together?
Yeah, in coastal engineering especially, but also across most of our civil engineering, civil works and military process that we do, I really look at it as like a 3-legged stool, right? We have the physical modeling, which we've been doing a long time, field data collection, which we've also been doing a very long time, and then really what's grown so much, in the last, 50 years is through numerical. And together, these 3 really create the tool set within those, the tool sets that we need to solve problems. And I can give you an example. I want to know, I want to design a solution for a given area, right? I need to know, what are the forcings? I need to know how big are the waves going to be, what are the currents going to be, or what's the flood going to look like? And really, a lot of those answers come from the fact that we've done data observation. And sometimes a lot of that's derived because we've done our data observations for a long time.
Sure.
So we have some historical reference to say, okay, this is what we can predict will happen, or we can have a probability of what will happen in the future.
Sure. Physical models, and of course that's what we're focusing on today's discussion. What are some of the situations maybe where they have the most value?
Yeah, so really there's like way to think of it is like maybe 3 different areas where they're really valuable. The first place is anytime there's fluid like water interacting with a structure. So whether that's a dam, a coastal breakwater, lock chamber, so you have complex geometries and you have water moving around those. That's a really good scenario. And the next area where there's a lot of value in the physical model is where you have water with either air or water with sediment or both. And so in those cases, sometimes it helps to have physical model because you can learn, how maybe the air entrainment is important, and that can be difficult numerically. So that may be a scenario where a physical model is really important. And the last thing on the research side is we can isolate very specific processes. And that can be valuable because you can learn how something behaves and you can test different things. And then you can use that information to maybe develop numerical models or systems portions inside of numerical models to make them better.
I think if I've got this right, maybe you mentioned the other day that physical models work best for a smaller, again, you mentioned seeing a specific area, and if you were looking at a whole system on a grander area, that's kind of where the numerical model makes
sense. Yes, 100%. So, we started with, we were doing like huge models, and like the Mississippi Basin model is an example where we're modeling the whole Mississippi River reach. Luckily, thankfully, we're doing that with computers now. We don't have to do that with a physical model. So now physical models are really focusing on how a certain structure performs in that system, or how an element of that system is going to perform. And we're not actually doing the whole reach. So call that near field type tool. And the far field tools are very much more better suited for numerical.
Sure. I want to get into maybe just to maybe paint a picture of some of the different kinds of projects that you do. And I want to start on the military side, which I understand has kind of been a growing portfolio for you all, more recently. You kind of talk about both some of the kind of projects you do, but also kind of how physical modeling can help the joint forces improve their readiness.
Yeah, so when we think about physical modeling in support of DOW, we have a couple of different instances where they really fits right in. The first thing we've seen a lot of growth area in is installation resilience. How are different coastal installations, which there's a lot of them, going to survive or going to perform when you have hurricanes or other coastal events happen that can damage those regions? So they're looking for solutions too. And so what we see is that they're needing help in testing solutions or deriving plans. And so we've been testing different solutions, both industry solutions and also through some other research program solutions to help to find ways to improve installation resilience. Second thing that we've seen a lot of growth in is how we operate, trying to understand how we operate safely in the nearshore area, excuse me. So when you think about operations across the spectrum, right, from the ocean to land, pretty much anywhere we go in the world, we're going to have to take a lot of stuff, right?
Sure.
When you're moving and you're doing logistics, you have to move a lot of equipment across a long distance. And at some point, that ship or that vessel or whatever is going to have to cross this, what we call the littoral environment. And so the littoral environment is very dynamic, and it's a lot different than the deep water ocean that, the Navy is often looking at.
Littoral would be closer to shore.
Much closer to shore, yeah. So right where the waves are breaking, the currents are often much higher, and that's a real critical zone. And interestingly enough, the Army kind of owns that space in a lot of ways when we talk about logistics. So it helps for us to know, okay, how is something going to get across that zone, whether it's going into a port, whether it's going onto a beach, doesn't really matter. And then how is the different Army assets or the other assets for the other commands, how are they going to perform across that region? So we can test those physical systems and understand what are their limit states, when can we operate safely, when is it maybe safe, and when is it definitely not safe.
Sure. And obviously, as there's been a growing focus, within the Department of War on what we call Indo-PACOM, the Indian Ocean, Pacific Ocean kind of area, that's a lot of water.
Well, the Pacific Ocean is only about half the Earth's surface, so it's a long ways to go. And there's a lot of military installations out there, right? Both Army and Navy and whatnot that we have out there. And so we need to think about those as there's a critical pieces of infrastructure. So there's an infrastructure component there. And, but at the same time, we have to move material around. We have to get there. We have to get somewhere else. And so when you really think about that, it's hard to imagine a way where any operations in that space is not really dealing with water.
Yeah, sure. And you all have done projects with across the various forces. I mean, obviously, it's an Army, but you've also done work with Navy and Marine Corps as well.
Yeah, so we've got a really great relationship, collaborative relationship with the Navy and also with the Marine Corps. And so we're able to look at different systems, maybe they're developing or different installations for those types of problems, and determine, okay, what can we do? How can we solve these problems?
Sure. Moving to civil work side, how can physical modeling help engineers design better projects, more resilient coastal defenses and whatnot?
Yeah, on the civil work side, it's really, twofold, right? There's two different things. The physical model buys down risk. So we reduce our uncertainty that the solution will work. And that's a huge thing, right? Especially when you're talking about taxpayer money. These projects are massive, orders of sometimes in the billions of dollar type solutions. So buying down the risk, getting the confidence that we know the solution will work. The second thing is a lot of times we can save money. And what I mean by that is we can find out, you don't need to build it that big.
Sure.
You don't need to do it like that. That's a huge cost savings. Oftentimes, you're looking at, you can save thousands, tens of thousands per linear foot of structure. And if you're building hundreds and hundreds of feet, you're talking about instantaneously, you can be saving millions and millions of dollars through these studies.
Sure. And the kind of stuff, again, we talk about various infrastructure projects y'all will test. I know there's a lot on, you mentioned breakwater or maybe a harbor improvement, or they're changing something on a dam and they need to make sure it won't mess up navigation, say, in that sense.
Yeah. Well, a lot of the infrastructure in the United States is aging, and we're looking to improve that infrastructure, not just based on what happened in the past, but what could happen on the future.
Sure.
So we're looking at, hey, how do we make our systems better? How do we make our infrastructure last longer? How do we get another 50 years, 100 years out of that? So that's a huge part of what we do is upgrading, right? The Corps has a huge number of dams, I think over 700 dams that we maintain and operate. So it's a huge number. But also on the coastal side, we see a lot of desire right now to build these coastal storm risk management projects, massive infrastructure projects to support and protect huge metropolitan areas all along the East Coast, especially in the Gulf Coast. So most of those systems need some type of seawall or breakwater, or gate structure. And so physical modeling can help us determine, okay, will the design solution perform as expected?
Sure. So actually, we've talked about military, talked about civil works, and one of the strengths of ERDC is its ability to leverage its expertise across both and maybe learn from the other and take solutions from military side for a civil works project or vice versa. I mean, do you have any like stories, examples? How much kind of interplay do you see between the two, and even having both make the other one stronger?
Well, it's funny, one of our facilities, for example, is an indoor beach.
Yeah.
So it's like a big beach, and it has wave machines, and we can generate all these different wave heights, and we can generate currents. And it was all built really originally for civil works. People said, "Oh, we don't want to understand civil works." That facility is almost 90% usage right now is for support military.
Yeah.
And so it's something that it's a one of a kind in the world, doesn't exist anywhere else. And, it had a really big civil works purpose, but now it's got a really big military purpose. It probably even bigger than its civil works, originally was anticipated.
Yeah.
So, we're just, it's a physical asset that we're like, hey, we can use this to solve problems across both sides. And you see these things also a lot of times in the physics we learn. You can take that physics and you can apply that that we learned in the physical modeling, and you can use that for solutions on the military side, whether it be installation resilience or asset dealing with physical assets. So that's kind of the biggest thing we see, is that we can leverage this research and instantaneously improve the other side, and that's been a big help, because a lot of our efforts, especially with natural infrastructure that have happened, now they're coming into play in this installation resiliency. So a lot of that was developed more for civil works, and we're seeing that rapidly move over to that world.
Sure. Like you said, you've got the expertise. You learn from one or the other, and that you can immediately apply it without having to call somebody that's done. Yeah, for sure. Facilities. Tell us, and you mentioned the indoor beach, and it's cool to see. For people who haven't seen it before, and audience. I mean, the sand and it feels like you're at a beach. There's a roof over you.
It was like you're at a beach. 100%.
Tell us that, and just all the other facilities kind of that you guys have.
Yeah, so CHL maintains around 1 million square feet of physical modeling facilities. About 60,000 of that is for coastal. And so you say, oh, that's not that much. And it's because, comparatively, and that's because the wave machines, you have to have these wave generators that basically can produce waves. You computer program it, and it makes the waves you want. And those are quite expensive systems. And so you can't just have them everywhere. So we have really a basin that can do like beach processes. We have a basin that can do coastal structures. We have two pretty large flumes. They're 63 meters long. And then we have another flume that's about 48 meters long. And so the nice thing about it is with the three flumes, we have kind of three different sizes, and so we can scale the project to be most effective across those three sizes. So some processes and some models, we need the smallest one, and that's the most cost-effective solution, but sometimes we need the biggest one, and so we can kind of move between those. And then on the inland side, we have, obviously we have the rest of that space, almost 940,000 square feet. And so we have these huge facilities, and we can build pretty large models. I think the largest we built recently is about 7,000 square foot model for a district support. So, you can build these really big models and look at all types of processes in them and help dial in the solutions, or how we need to operate this, or will this work? So it gives you a lot of options.
Yeah, that large model you just mentioned, can you say what it was?
Yeah, that was McNary.
Okay.
Yeah, that's the McNary
Locking Dam.
Yes.
Which is, remind me where that is, Kentucky?
No, that's on the Columbia.
McNary, okay, gotcha.
It's on the Columbia River.
Yeah, sure. But, so even to kind of explain, people not familiar, when you talk about these giant inland models, a lot of that is because it may be a locking dam in a specific river system. So you've got to kind of get the upstream and the downstream and kind of model a lot of that.
Yeah. So a lot of times you'll see, you have to have enough upstream so that the approach is correct so the flow is moving correctly toward the structure. And then you have to have, a lot of the downstream, because that's usually where the concern is, or the attention is, whether it's the spillway or just downstream of that. So we're kind of working through that. So, we have a lot of models on the Columbia River system, the Snake River. And then we have a lot of models. We have, models that are kind of spread across the rest of the eastern United States. One of the largest models we have right now is the Garrison Dam model. That's for the Omaha district. and that's the largest dam in the Corps of Engineers inventory, and it's going through a process to, rehabilitate it.
Yeah, sure. Going back to coastal, you talked about the wave machines, and I know that's a big part of this. And it seemed like I even remember talking about it in the past, that you can do regular waves, irregular waves. I mean, talk about just some of the unique abilities that those give you.
Yeah. So if you think about coastal engineering, I don't know, 50, 60 years ago, you could only really produce one wave of a known period and wave height. And, so what it mean, it would just look like the same wave coming one next, one the next, one the next, one the next one. But if you ever go to the beach, it's not in the same wave, right? Every wave's a little bit different than the one before it, and sometimes the waves are kind of interacting, and you get a little bit more run up this time. How far the water travels up the beach than the next time, and so the process isn't really regular. And so a lot of times that's commonly known as like an irregular wave train. So it's a compilation of waves of different frequencies and amplitudes, and they're all moving together. So that's realistically what's happening in the real world. So we model that, and you can input the shape of the energy into the machine, and then it can derive, okay, this is an example of what that wave time series would look like. And so it brings some complication factors in the sense that for a regular wave, if I run the regular wave, it'll be the same wave. So if I run it a couple of times, it's really the same wave. I can run it more, but ultimately it's just the same thing over and over and over again. When you have this variation in time of what the wave frequency and the wave height is, you have to run for much longer. So what you see is, you come over and you go, wow, you're running this for a long time. It's like, yeah, we have to run it for so many waves. So we try to build up enough waves to have a statistical picture of, okay, this is what's going to happen.
To give you full validation.
Yeah.
Full picture, I guess.
Yeah.
Makes sense. Interesting. Another important piece of this that we hadn't really talked about is the fabrication shops.
Yeah.
That ERDC has. In fact, we just did a podcast episode on that recently, and Zach Smith was talking about the teams there and what they bring. Talk from your perspective. I mean, their ability to build various models for what you need, and the specifics, the craftsmanship, and what that enables you to do.
Yeah, my opinion, that craftsmanship and their capability is pretty much unrivaled. I've never seen that much capability anywhere. And so, we can build models, we can replicate models so well here comparatively. And, it's not to say that others can't, it's just that we have so much talent and capability there between the shops that Zach's over. Whether we're building a boat hull, or we're doing a dam, or we're building, the structure to support all that from the welding shop, or the turbine models that the machine shop's building. These things are so important that we get those correct, because when you talk about bringing a system down to scale, it's so important that the geometry is preserved. So we try to keep that geometry just right. And as you bring it smaller, little errors start to add up, and it's starting to look a lot larger. So I can give you an example on that. Let's say I build a model and I'm off by an inch, and it's a 1:48 scale, just saying. That means that everything in the model that's 1 inch is 48 inches in the real world. So now I'm off 4 feet. And so now you can see how it becomes really important that we can able to shrink those errors down. And the shops give us that capability because they've got the tools, but they also have the experience on how to build things and assemble things in a way that are really meaningful and make the projects work.
Yeah, and the experience.
The
precision. So that's neat. So I guess we've talked around it in different ways, and we talked about all the capabilities, but what makes ERDC unique in this space and in their ability to execute coastal physical models?
Yeah, there's a couple things that are unique for ERDC and coastal physical modeling. One thing is we have a wide range of scales in our facilities. We talked about that. We can do kind of smaller things in these flumes and larger things. These flumes, not everyone has all the scales available to them. The other thing is our craftsmanship is pretty much unparalleled in that regard, and we can. And another big part of that is we can couple what we do in the physical model with the laboratory. I mean, with the numerical, excuse me.
Yeah.
With the numerical effort. So we can bring in experts that have, experience running wave models and other high fidelity CFD models to really explore things that we can't necessarily see directly in the physical model. And we have a lot of experience. We've been doing physical modeling in a coastal environment since at least World War II. And so we've supported the development of so many ports in the United States, the largest being LALB, Los Angeles, Long Beach. That was a huge achievement for the U.S. to build that facility. And so when you think about it, we have a really a wide range of capabilities we can bring together to really give the U.S. and the DOW the tools they need to make decisions on and design solutions for tomorrow.
Sure. How much are you working with other laboratories and other, again, you mentioned being able to call on even numerical modeling experts within CHS, I mean, across disciplines too, but yeah, kind of how much do you kind of see that cross-pollination happen?
Yeah, I mean, that's a great thing about ERDC is you got so many labs with so much expertise. And, we think about, I need someone, we're doing a project and, we need someone with expertise in levees and levee soil mechanics. We can go to GSL, and there have been some of that in the past. We're doing some military engineering work. We have expertise in the floating part. We can go to GSL and get someone to help us. And they're leading on the structural side, the structural analysis of those components. And together, we working together, we can build a complete picture. So if there was just us by ourselves, we couldn't do that. And if they were by themselves without CHL, they couldn't build that complete picture because they couldn't, don't have the equipment and the facilities for the water side. And then obviously, the ITL with the supercomputing power, that's a huge advantage. I mean, that's just it's a huge force multiplier to have that capability at hand and all the systems inside of it that really support like computational fluid dynamics and things. So, and the list goes on, EL, a lot of huge collaboration there with installation resilience. I can't say, how much they are major partners in all of those things, especially for natural infrastructure, particularly. So when we just look across the ERDC, really the biggest success stories are often when it is multi-lab.
Sure.
So
that's what we call Power of ERDC. It's, kind of the whole greater than the sum of the parts.
Yeah, 100%.
Yeah, sure. On the theme of collaboration, how much are you all working as well with outside entities, industry, government entities, academia, and so forth?
Yeah, well, it's like, I think I'm on record talking about how important our academic partners are. Obviously, ERDC and CHL has a huge amount of coastal engineering talent and knowledge and experience. But the field is big, and so academia allows us to keep, seeing kind of where other things are heading, grow rapidly in areas that are developing fast, because they're pushing sometimes the limits and they have different funding sources and things so you never know. So it's important. Industry is obviously really important because a lot of times industry has, pathways to move things into practice faster than sometimes we do. So it's always important to kind of see what's being developed there, what's being worked there. And we often do testing for industry. Somebody will come up with a good solution and they want to test it and get the data to validate it. And we'll provide those testing services to do that. And then lastly, we have CRADAs, which are cooperative research and development agreements. And so in those instances, we're working to kind of build joint knowledge and joint capability. So all those tools are huge. All those relationships are huge into keeping ERDC in a position where, we are providing the best solutions.
Yeah, sure. Looking ahead, kind of where do you see as some of the biggest coastal engineering challenges in the next 5-10 years, and kind of how is ERDC kind of helping prepare for this?
Yeah, well, I think ERDC's been doing a really good job in kind of moving the coastal engineering field to a probabilistic type mindset. So there's a big group at CHL who's really been pushing that. Okay, we can't think of things in just, I want to design for the next Katrina. More, it's important to think, okay, let's design for some type of probability event, and how do we document that and how do we build that? And that's important. And then that feeds back into what we do in the physical model, because we have to be able to model those things in the laboratory. So working together with them, and they're pushing things. Other things that are coming around that are really, there's still development in computational tools that, I'm like, oh, that's amazing. Even GPU-based processing and things that are really driving how fast we can set things up. In the past, for example, we would do the physical model, hand it to the numerical side. They would look at the data, they would validate against it, and then they would say, okay, and it was kind of one way.
Yeah.
And now we can do some of that stuff on the front end. And so now it's becoming even more integrated across, it's like, I almost can see a future where the data that's coming out of the numerical model is telling the physical model, hey, do this. And they're iterating to a solution even faster.
Sure.
And it's more of a, almost a data feed between the two systems. And that sounds kind of wild, but I think there's nothing really, because everything we do now, data collection, how we tell the machine, everything's digital. So in that sense, it can all be told what to do. You can tell a computer what to do. So that leads to automation. So we can automate things and automate systems. So I think that's a huge technological development that could occur. And there's others in the world that are looking at it. So I know it's probably likely to happen sooner or later. Yeah. So I think that's a big advantage, that we have going forward, if we continue to maintain and grow how we can couple these numerical systems and our physical systems.
Sure. And that each of them feed off of the other,
right.
What they can offer, inform each other. Yeah, sure. Interesting. Anything that we hadn't covered that you want to make sure we talk about or highlight?
The only other thing I would talk about that we haven't covered is, we talk about building the models, and we talked a little bit about the shops, but the other thing that's really important to notice, how we build models is so much different than what we did 20, 30 years ago in the Wellmos methodology that we developed. So, we have our own patented system to build models. Obviously, other federal laboratories are using it. And that's allowed us really unprecedented accuracy in what we can build, and how especially these large models, we can get them so much closer to reality than we've ever been able to in the past. Yeah.
So, and I'll start just to explain to people who aren't fully familiar with what you're talking about. And we talked about it also with Zach a couple episodes back. I think it was episode 46. If anyone wants to go back and listen to that. But previously, they were concrete models, correct? So you're having to build them huge concrete structures by hand, and now it's kind of foam and cut CNC machines and so forth.
A long time ago it was dirt. We used to build the models out of dirt, which is crazy to think about. And then we moved to concrete, and concrete, it was almost artistry. Somebody's out there looking at contour lines, and it was amazing. And really, you go back and you look at what they did, it was amazing. It's amazing they could do it that way. Yeah, really. But now it's all computer aided, so it's just, I can take bathymetry, I can process that in a computer, I can generate the contour maps, I can generate the points, and I can feed that directly to a CNC machine. And, we can just route that bathymetry directly. And what that really creates is an accuracy where in the past we only had control points, and that's where exactly where you're at, about every 4 feet. So in between those 4 feet, maybe 2 feet, depending on the model, you were kind of just hand molding what you wanted. And if you had a model with a lot of bathymetric changes, you could be off a lot, because you're just you could shoot points in and shoot elevation in for certain points, but that was a lot of work. But now you just CNC it all.
Precise, yeah.
So it's really a lot more precise methodology.
And it gives you, as you said, just so much more ability. And your ability to test things, and in precision, I guess.
Precision, and accuracy is so much higher, and so that's really been a game changer, because it's a little bit less workforce. We lost a lot of the guys who did the old concrete. They just retired, so we lost a lot of that skill as well. So it would have been really difficult to hire in people and say, oh, I know you've done driveways your whole life, or you finished floor, and now say, okay, now I want you to make art. It's almost like an art form, and it's really hard. Yeah. So moving that pathway, and these guys, they know how to run the machines, they know how to make sure and check everything as they go. That's really been a huge advantage.
Sure, I go, well, it's not an easy process to switch from one to the other, but like you said,
Yeah.
it's been a game changer.
And I think since we've switched, we've done, I think we're over 30 models.
Okay. Wow.
Since we've switched to that methodology.
Yeah. Cool.
So,
well, thanks for joining us today. That's all we have for today, but appreciate you coming and sharing more about physical modeling, and thanks for all the work you and your team do. Doing like we've talked about a lot of important stuff for the nation and the warfare. So thanks for what you do, and thanks for coming and joining us to talk about it.
Appreciate. Thank you for having me here.
Yeah, and for our audience, thanks again for joining us. To remind you, you can look for a new episode every Tuesday at 10 o'clock. Those videos drop on ERDC's LinkedIn page as well as on ERDC's YouTube channel. And then you can also find all of our episodes in various podcast players, whichever podcast player you like to go to, or go to poweroferdcpodcast.org. It's kind of one stop that's got all the different resources, all the videos, all the audio episodes, as well as different resources and links and ways to get more information. We'll have some from this topic and kind of more information about physical modeling at ERDC and so forth. So thanks for joining us, and until next time.